So getting back to how strong is strong enough, well, back in 1994, just 12 years ago, it took an engineer about $20,000 in parts to build a computer to crack a 40-bit encryption algorithm. And they did it in 3.5 hours. That's 1.1 trillion keys. Today, 2016, that same computer to crack a 40-bit encryption algorithm costs $14 to make, a Raspberry Pi. And they can do it in literally tenths of a second. The level of encryption used is largely determined by time. How long does it take the data to be broken, and also how long does the data really need to be protected? If you have war plans, you only need protection for a short period of time, because once you start the attack, hey, they know you're coming to the beaches there, and it's no longer a secret. But some trade secrets, like Coca-Cola, things like that, have an infinite period of time it must be protected. They may require periodic encryption updates just to break up to higher levels. In the past, 40-bit was very good, but then as computers got better, oh, we have to switch it now to 56. Now we have to switch it to 2056. So like anything else, encryption has to change and be updated just like anything else, just like an operating system or application software. Another thing they think about when trying to determine how strong is strong enough for encryption is who is the data being protected from? Is it a child? Minimal level of password protection is needed for something like that. Is it a spouse? Are they a propeller head? A hacker? 256 or 128-bit encryption should do the works, because it will take them a while to break that. Or is it a powerful enemy? What are the resources of that enemy? Do they have a football field size room of nothing but high speed GPUs all running in concert to go after a 2056-bit encryption? Like anything else, it's a combination of time and money. Unlimited time and unlimited resources or money, you can break any type of encryption. So how does encryption really work? Well, there's quite a few techniques, and it depends on, once again, what you're trying to protect. You have substitution, A for B, Q for A. You have transposition. That means every time you see an A, you transpose it to a C, 3 letters up. You have a combination of both substitution and transposition. Things like, instead of, whenever you have a L, lowercase l, you use an exclamation point. Or anytime you use the number 3, you use an E, and vice versa. If you have the letter E, then you use the number 3. All those combined with maybe a mathematical function, and of course that varies with algorithms and logarithms, and these can be performed on a computer system. All that are the basics as to how encryption starts. Let's talk about substitution, where we replace each character in a message with another one, such as, hey, the HAL 9000. That was actually a play off the term IBM 9000, which was a computer at the time that 2001 Space Odyssey was created. They just subtracted one character from I, or one character from the 3 letters, and they came up with HAL. So I, A, B, C, D, E, F, G, H, I minus 1 is H, B minus 1 is an A, and so on throughout the alphabet. This was pretty common during the radio days, World War II, World War I, even back in the days of the Civil War, because of decoder rings. If you had the ring and you set it at the right place on the ring, then as you went around and looked at the letters, you could see what letter was substituted for another letter. And they can be increased or decreased by any value. So let's say you had the letter A and the key was 10. Then you would have to go 10 letters up. Transposition is scrambling of the characters. This is commonly used in newspapers and puzzles and things like that. Sometimes it can resemble a foreign language, and people will start looking to translate a foreign language rather than realizing, No is just a transposition of the characters. An example of that would be the word read. Let's say your rule set says that you move the first two characters of a word to the end and the last two characters of a word to the beginning, and then reverse the order of those first two characters. So READ would be RE at the end, then you would move AD to the front, but then transpose the AD into DA, and you would have the word there. So now we know that good encryption programs use a combination of both transposition and key length. And sometimes they also compress the data, like a zip file compresses data. That makes the process a lot more complex to try to decrypt. And also it makes the encrypted file smaller most of the time, so that the actual true length of the file is not known. So up till now we've been talking about the easy side of encryption. Let's start talking about encryption algorithms. There are two kinds of algorithms used, and they're referred to as one, symmetric key algorithms, and then the other one would be asymmetric or public key algorithms. The asymmetric or public key algorithms are ones that we see the most common in the marketplace today, and they were a strong leap forward when it came to encryption. It is not uncommon for encryption programs to incorporate both types of algorithms and create a hybrid, sometimes referred to as a symmetric public crypto system. Example of that would be PGP. So in symmetric key encryption, basically that is divided into two categories also. There's the block and stream. Block algorithms encrypt data one block at a time. That would be like a sector on a hard drive. All 256 bytes are encrypted using a specific key. Then you have streamy algorithms, which encrypt an entire file byte by byte. So every single byte is transformed or encrypted in some form one byte at a time. So the entire file is encrypted one byte at a time, and it makes it harder to decrypt files like that. It also takes longer to encrypt a file byte by byte. Stop and think about it. A block algorithm can take a look at a block and it encrypts it now. So that's one pass at the encryption. Whereas this byte by byte algorithms would have to do it 256 times, like on a sector on a hard drive. Symmetric key encryption also uses a single key. That means one password. It's the same password you use to encrypt it and the same password you use to decrypt the message. Good examples of that are the DES decryption standard, Triple DES, Blowfish, IDEA, which is the International Data Encryption Algorithm. Some other examples of that would be when you encrypt an Excel file or a Word file and you give it a password, and you have to use the same password to decrypt it. So let's take a look at the symmetric key encryption process as a whole. We'll have a plain text message. It'll go into the encryption process where you apply an algorithm and a key, and then it comes out on the other side as ciphertext, which is basically the encrypted plain text message. So now we have the decryption process where the ciphertext comes in. The same key that was applied to encrypt the message is now applied with the algorithm to decrypt the same message, and the original plain text message is now produced. So what are some of the pros and cons to symmetric key encryptions? It is fast. It's probably one of the fastest ones you can do, and it is considered the workhorse of encryption. The cons, well, it's a single key approach, and it requires a secure method for the key exchange. You have to remember, the more people have the key, the more vulnerable the key becomes. It's like a secret. You have to somehow get that key to the person on the other side without anybody seeing the key. And how do you do that?